So, problem number 1. An astronaut on the moon receives a message from mission control on Earth. The signal is sent by a form of electromagnetic radiation that takes 1.28 seconds to travel the distance between Earth and the moon. What is the distance from the Earth to the moon?
I don't think this has anything to do with the person.
This here is very much chapter 2 of the textbook. It's not relativistic. It's simply how do you relate distance with time?
Velocity? Thanks.
Yeah. What's the speed of the radio wave or the electromagnetic radiation?
It would be V equals D over T, or delta T.
Well, no, I mean, an electromagnetic radiation traveling through the vacuum of space.
Like the speed of light?
That's right.
Okay.
In any reference frame, the speed of an electromagnetic wave in vacuum is the speed of light, which is, and we only have 3 sig figs, so I'm just going to put 3.00 times 10 to the 8 meters per second. Okay. Since we only have 3 sig figs, why have more? Okay. So that's going to be 3.00 times 10 to the 8 meters per second. Excuse me. Times 1.28 seconds. Actually, usually I'd put one more. It'd be 2.998 times 10 to the 8 to get it one more. So that we don't lose anything. There is a good reason to have one more. So basically, 3 times 1.28 is
3 times 1.28. And 3.84.
Yeah. Okay, so that one wasn't very tough.
Come on, Dr. Beth.
That's a starter.
Okay.
Well, we'll get into something more maybe. What is the postulate? Well, this one here we don't even need to copy. What is the postulate having to do with the speed of light on which the theory of special relativity is based?
Like Einstein's second? Well, he has 2 postulates, and there's one that like everything, like the speed of light is always the same, like in every reference frame.
Speed of light in vacuum.
Oh, in vacuum.
That's kind of important because, speed of light through glass is not the same.
The speed of light in vacuum is always the same for every reference frame. And then there's another postulate that says something about the like relative measurements or something. It talks about
the laws of physics are the same in all inertial reference frames.
Okay.
Those are the 2 postulates, and it's good that you have those.
Thank you. Yeah, I remember reading over those.
I'll get you in class, you know it too.
What?
Soccer. My team had a very epically bad weekend.
Here? Like, is it which team?
Manchester United.
Oh, okay.
Actually, weekend. It started during your debate when they lost 3-0.
Oh, because he was watching it.
Well, he wasn't watching. I think he was just looking at update. But and then over the weekend, they could have won their league, and they were up 2-0, and then they gave up 3 goals and lost 3-2. They're still going to win the league.
Of course.
Okay, we only have 5 minutes. So find the value of gamma for the following situation. An Earth-bound observer measures 23.9 hours. So we have delta T as measured on Earth is 23.9 hours. Now, I haven't read enough to know anything else about this time, if it's proper time or not, to pass, while signals from a high velocity space probe indicate that 24 hours have passed. So delta T for the probe is 24.0 hours. And the question is, find gamma. So what's the first thing you need to determine before you find gamma?
What is gamma? Like, what is... I need to determine the proper reference.
Yes, the first thing you need to do is determine which is the proper reference frame for time, because these are time measurements. So name how you would do that.
Well, there's Earthbound observer, but he measures something that is going out to space. But he's earthbound, so I don't think that's going to be right. I think it's going to be this, but the space probe, it indicates that I think that one will be the proper time, because it's like the actual thing that's like flying, or the thing that has speed. Even though it should be, for us, it'll be like constant speed. For special relativity, it can't be accelerating, but because the earthbound, the person on Earth is observing it going into outer space, and it can't like tell the time during, and like it's seeing it at a different time.
Okay, I think you hit the high points, but let me make sure that we have that for one of the two ways of determining. The other way is going to be easier here, but it's not absolutely correct. The other way presupposes that one of them is the proper time. So the way that always is correct is the one that you were angling at. The proper time is measured in the reference frame where the measuring device is with the measured thing and stationary. So the measured thing here, an earthbound observer measures 23.9 hours to have passed, while signals from a high velocity space probe indicate that 24.0 hours have passed on board. And so we don't actually know what the measurement is. Are we measuring something that's happening elsewhere? We don't actually know what we're measuring. So this one here kind of fails because we don't know what we're measuring. It's kind of a poor problem, actually, because you really need to know what you're measuring to know if either one of these is the proper time.
Yeah.
So what we're going to do is go to the other one, which presupposes that one of them is the proper time. We have time dilation. Whoops. Turn off the auto shapes. Time dilation, which means the proper time is always the shortest possible time. Yes. Between events. So if you have two different times, you can't say, we're going to do it here, but you can't say the shorter one's the proper time, because there may be neither one's the proper time. But if you know one's the proper time, then it's going to be the shorter of the two. And so we're just going to have to take it on faith that one of these is the proper time.
Okay, so I don't know how is the second time that's not the speed, or it isn't with the object? Is it?
Well, we don't know what's being measured.
Okay.
That's the real flaw in this problem. If we're measuring the time that it takes for you to brew your coffee on Earth, then the person on Earth is clearly measuring it. If it's the time for the coffee to be brewed in the spacecraft, then the person in the spacecraft is going to be measuring the proper time, right? So we just don't have.
Okay, gotcha.
The perspective here.
That's a nice rule, though, that I wasn't aware of.
So we're going to say delta T probe is equal to gamma delta T Earth, right? Because we identified the shortest time is delta T Earth just by looking at the two. And so delta T with a subscript of 0 is how we usually designate the proper time. So finally then, gamma is just delta T probe over delta T Earth is equal to 24.0 hours divided by 23.9 hours. What's 24 divided by 23.9, just so we can get a number?
23.
0.9.
We got 1.004. 24 divided by 2.
All right, we got 3 minutes until my meeting.
How did you know? So, in the textbook, it has like this equation. How did you know to do gamma times delta t?
How did I know to do?
Okay, so
that's the
what we're
equation
looking
for time dilation.
That is.
This has a follow-up question. What is unreasonable about the result? Gamma cannot be less than 1. Well, I presupposed which one had to be which to make sure gamma was bigger than 1. Right? They didn't give me enough information to determine, or else we would have had that. So there's an inherent flaw with that one. And then it has which assumptions are unreasonable or inconsistent.
Okay.
Let's just move on to the last of the ones here.
But this equation right here is for time dilation.
Yes, that's the time dilation equation. That's the one.
Could you write it really quick?
All right, I will.
Sorry.
As soon as I get this copied.
Sounds good.
I believe I hear the voices of the people who are coming to see me.
Yeah, I have class too.
So the equation was delta t is equal to gamma delta t. So yes, come on in.
Are you available?
I am.